SwayamPrabha. Digital India. Educated India.
Today we shall discuss about the first law of thermodynamics for a flow process across the control volume. You know that in the last class we were discussing about the first law of thermodynamics for a flow process across the control volume, and we have established the mathematical expression of this equation in the rate form. So, if we try to write that equation, first law for a flow process across the control volume. So, if we write this equation, in fact, in the last class we have derived the expression, that is q dot minus w dot equal to d dt of Cv plus the flux term what we have written in the last equation. This is what we have written in the last class. Today we shall discuss that if this equation can be applied to a special process and that process is steady state steady flow process, then what will be the mathematical form of this equation. We have also discussed that to arrive here we have taken one important assumption is that you know that the properties are remaining invariant over the cross section through which flow is occurring. So, if we consider a control volume, say this is inlet and this is I and that is outlet, that is E, exit. So, the flow is taking place and this is the control volume. So, this is control surface and this is Cv. So, over this cross section the flow properties are remaining same. So, this is one important assumption. Flow properties are remaining the same over the cross section. If we have multiple inlets and multiple exits, we also need to consider this assumption that the flow properties do not vary over the cross section. So, now taking this assumptions we could arrive here, and this part, if I use this part, you know, so basically you know that rho Vr dot eta cap dA, that is mass flux, which is multiplied by this term. So, you know that again if I try to mark it using this color, that this term basically the internal energy plus the energy required to maintain flow in the presence of pressure both at the inlet and exit. So, this is very important to know, because again I am telling the equation that we are going to derive today is an important equation, and we shall be using this equation in different cycles that will be discussed in this course, in particular in the power cycle. So, this term rho Vr dot eta dA, if we integrate over the control surface, it is the mass flux. So, mass flux in minus mass flux out, and this term is multiplied by this term, right, H plus c square by 2 plus Gz. So, this is specific energy, that is specific internal energy plus energy required to maintain the flow in the presence of a pressure, So, I am writing this H plus c square by 2 plus Gz, right, H plus c square by 2 plus Gz. So, this is internal energy plus energy required to maintain the flow. So, that is flow energy. So, that is the flow energy you have probably studied in fluid mechanics course, that is the internal energy plus energy required to maintain flow in the presence of pressure. Okay. So, today as I am telling, because just we have recapitulated what we have discussed in the last class, starting from this equation, if we try to go to derive the equation for a special process, and that special process is steady state steady flow process. So, if the process is steady state steady flow, then what will be the form of this equation? So, I am writing first law of thermodynamics for a steady state steady flow process across the control volume. You know that I have underlined these two coupled keywords, that is steady state steady flow. So, we shall discuss the significance of this particular two keywords in the context of the analysis that we are going to do today. So, again let us assume that we are having control volume, and this is having, so this is inlet I and that is exit E. So, flow is going into the control volume and flow is coming out from the control volume. So, this is control surface and this is CV, and if we use this particular assumption that the flow properties do not vary over the cross section, we may have multiple such inlets and exits. So, even if we have multiple inlets and exit, flow properties which are the properties, if we go back to the slide, we can see there are properties like enthalpy, velocity, g, that is height of the cross section, and g. So, basically h, v, g and z. So, these 4 properties like h, c, g and z do not vary over the cross section. And if we take this, then we can write, as I told you, that first law q dot minus w dot equal to d dt Cv plus. So, if this is not varying over the cross section and the mass flow in and mass flow out, that will be, I mean, this integral Cs rho Vr dot eta cap dA, that is nothing but the mass flux. So, if it is at the, if we apply this at the inlet, so this is mass flux into the control volume. If we apply at the outlet, that is mass flux out from the control volume. So, I mean, if these properties, I mean, if these properties are not varying over the cross sectional area A through which flow is flowing, the flow is flowing and entering into the control volume, then what we can do, we can take it out and simply we can write that M, as I told you that I can take it out, and Vr dot eta cap, this is positive for the outflow or at the exit, and Vr dot eta cap, that is negative at the inlet, because this is a normal pointing outwards from the control surface. So, the dot product will be negative for the inlet and it will be positive for the outlet. So, you know that I can write, that is m dot E. If we take this at the exit, so we can denote enthalpy, velocity and z at the exit. So, basically He plus c square by 2 plus gze minus m dot I into Hi plus Ci square by 2 plus Gzi, right. I have taken this summation sign because we may have multiple inlets and multiple exits. So, accounting for the possibility of having multiple inlets and multiple exits, we have considered the summation sign. I hope you have understood. So, basically this is the first law of thermodynamics. For till now we did not say anything about the process is steady state or steady flow, but this is the first law of thermodynamics for any process across the control volume, and we have written another form of this equation over here. So, just by rearranging we can write that I mean you can take W dot in the right hand side, but one important assumption is that the flow properties do not vary over the cross section through which either flow is entering into the control volume or flow is getting out from the control volume, that is at E. Okay. So, now together with, I mean that we also can write the mass balance equation. So, mass balance equation, if we write, that you have seen in the last class, that is dm Cv by dt plus m dot E minus m dot I. So, this is mass balance and this is the equation which is essentially for the energy balance. So, if we now apply this equation for the steady state steady flow process across the control volume, now say if we start with the mass balance equation. So, this is mass balance. And this is energy balance. Okay. So, if we start with the mass balance equation, so 0 equal to dmCV dt plus m dot E minus m dot I. That is what we have discussed in the last class. Now, see, we are going to have this set of equations essentially for a process, and that process is steady state steady flow. You have studied about steady flow in the context of fluid mechanics course. So, what do you mean by steady flow? Steady flow is a flow in which the flow properties do not vary with time at any given space, at any given location. So, if it is steady flow, flow properties do not vary with time at any location. So, now you know that we have considered the flow inside the control volume, and if we consider that this is inlet and this is outlet. So, inlet and outlet is remaining fixed, and if we apply the steady flow assumption, so we can write this dmCV dt equal to 0. See, I mean, so this is that if we go back to this equation, so rho Vr dot eta cap dA, right. So, this is the control or the control surface, and this is the control volume. So, if you try to recall the Reynolds transport equation, del T of rho dV, right. So, you know that if we try to write the first term of the Reynolds transport equation, I mean right hand side of the Reynolds transport equation. So, this is del T control volume rho eta rho n, then it is dV, right. So, if we try to recall this in the context of the Reynolds transport theorem, we can write this equation. You know that mass balance, can you really write that dmCV dt will be equal to 0 if the flow is steady? So, this is very important that that you see that the small n equal to 1. So, if you try to write this equation, I mean to obtain the mass balance equation, we consider eta, because n is abstract, it could be any property. If n is equal to mass, then small n is equal to m by m, that is 1. So, essentially the first term is del T CV rho dV. So, that is the m CV. So, now question is, so this is that is m CV. Now, if rho is not changing, steady flow, that is flow properties do not vary with time. So, rho is also an important property of the fluid, so it will not vary with time. If rho is not varying with time, then definitely mCV will not vary with time, then this term will be equal to 0. So, the consequence is that consequence of steady flow is that dmCV dt equal to 0. So, from this mass balance equation we can write m dot E equal to m dot I. So, this is the consequence. Remember it, because again I am telling, when we shall start discussing about the cycles, power cycles, refrigeration cycles, different mechanical cycles related to the thermal system, we shall be applying the steady state steady flow processes, and if we apply steady state steady flow process assumption, then from the mass balance equation we can write directly that m dot I equal to m dot E. We have taken summation considering the fact that we may have multiple inlets and multiple exits. Okay. So, now if we go to the energy balance equation. So, now see, we have already considered steady state assumption. So, basically for the steady state steady flow process, so basically this is a special process, we have already taken into account steady flow case. So, now remaining is steady state. So, if we apply that energy balance, if we write energy balance equation, energy balance equation. So, in that case we have just now see q dot minus w dot equal to del E dt C V plus, I am not going to write again in this integral form, rather we can write the form that we have derived just now, that is m dot E H E plus C square by 2 plus G Z E minus m dot I H I C O S square by 2 plus G Z I. So, this is the equation. So, this is C I. Okay. So, if we write it now, we shall be using another coupled keyword, that is steady state. So, what do you mean by steady state? Here the steady state refers to the steady energy state. So, here steady energy state. So, here steady state refers to steady energy state. If I try to explain it even more, then it indicates that energy within the control volume does not vary with time. So, basically steady energy state, it indicates that the energy within the control volume does not vary with time. So, if we write it that energy within C V does not vary with time. So, if energy within the control volume is not varying with time, we can make this term equal to 0. So, that means accounting for this steady state case, this term will be equal to 0. Energy within the control volume is not varying with time. So, that is d dt C V equal to 0. So, you know that we are left with this equation. So, energy balance equation we can write q dot minus w dot equal to m dot E H E plus C square by 2 plus Z E minus m dot I H I C I square by 2 plus Z G Z I, right. So, this is the equation which is obtained for the steady state case. So, this is the energy balance equation for the steady state. You know, I would like to discuss a few important critical issues which is involved with this particular equation. So, you know that this is, let me write it. So, this is energy balance equation, and from the last slide we have seen that mass balance equation can also be written like this: summation of m dot I equal to summation of m dot E. Okay. So, this is, so you know that this is basically, as first law talks about the conservation of energy. So, this is first law of thermodynamics applied to the steady state steady flow processes but in the rate form, in the rate form. So, this is the rate equation of the first law of thermodynamics applied to for the steady state steady flow processes. I am writing SSSF because if we go here, you know that if we take S steady state first letter from these two couple keywords, we will be getting SSSF. So, for the steady state steady flow processes, this will be the first law of thermodynamics in the rate form. I would like to discuss, you know that we have written that for the energy state dE by dt within control volume equal to 0, and this is essentially for the steady state, that is what we are discussing, right. So, we are discussing this is for the steady state. Now, see why I would like to do this exercise, you know that this E is the total energy. So, this is nothing but m into specific energy. So, if this total energy is needed to be time independent. So, if the total energy does not vary within the control volume with time, so that means mass also should not vary within the control volume with time, as well as the small e will not vary within the control volume with time, right. So, I am coming to the next slide. What I am telling that for the steady state d dt Cv equal to 0 and E being the total energy can be written m into E, that is nothing but m into H plus C square by 2 plus Gz, right. So, what I would like to tell you is that if we need to make the quantity 0 considering the assumption of steady state, then you know that the total energy will not vary within the control volume, that is what we have discussed. If total energy has to remain constant within the control volume, I mean if the total energy has to remain invariant with time within the control volume, mass within the control volume will not change, rather should not change, as well as the specific energy, that is h plus velocity together with this properties should not vary within the time. So, you know that what I am telling. So, steady state implies that mass within the control volume will not change with time. If mass within the control volume has to remain constant, density will not change with time, that is what we have learned. So, that means the steady state requires that mass within Cv should not change with time. Will it suffice, rather if mass does not change within the control volume with time, is it sufficient to ensure that we can write d Cv dt will be equal to 0? No, because it may be there may be a case that maybe mass is remaining within the control volume, it does not change with time, but the properties may vary with time. So, the product may vary with time. So, most important part is that if we need to ensure that the steady state, that is steady energy state, that means total energy within the control volume will not change with time, it necessitates that the mass within the control volume should not change with time. So, what does it physically mean? Flow has to be steady, right. So, that means try to understand, if you would like to ensure that the state will be steady, which in a way requires that the flow has to be steady. So, that is why the couple keyword steady state, steady flow came into the picture, right. So, if it might be a case that mass within the system is not changing within the mass within the control volume is not changing with time, but these properties vary with time. In that case, it would be steady flow with unsteady state, right. Try to understand. So, possibilities are there, possibilities. What are the possibilities? First is, number 1 is steady flow with unsteady state. Number 2, steady state with unsteady flow. So, if maybe the properties are not varying within the control volume with time, but mass is varying with time, even then we shall not, rather we can't write that d dt Cv will be equal to 0. So, try to understand, to have d Cv dt equal to 0, mass within the control volume should not change with time. Also, the properties do not vary with time, right. So, this is only important message that we get from today's class, is that if we need to have steady state, steady flow should be there, otherwise we cannot ensure that it would be steady state. So, even if the state is steady, but if the flow is unsteady, that means steady flow, that means mass is not changing, but unsteady state. So, this quantity that is properties are varying with time, in that case d Cv dt will not be equal to 0. So, for this case also dE by dt Cv not equal to 0, for this case also dE by dt Cv not equal to 0, because state is steady, but flow is unsteady. So, maybe this quantity is not changing with time, but mass will change with time. So, you can write that dE dt Cv will be equal to 0. Last case, say if we even ensure that the steady flow with steady state. If the flow is steady, m is not getting changed. If the state is steady, properties are not varying with time. So, we can write dE Cv dt equal to 0, but there again may be a case that even though mass is not changing, properties are not changing, but their product might change. In that case also we cannot write that dE dt Cv will be equal to 0, right. So, important is that steady state, steady flow, that means if we need to have steady state within the control volume, the product of the steady flow and steady state will be equal to 0. So, that means flow has to be steady, together with the properties do not vary with time, but their product should not vary with time. So, it is not a case that the steady flow with steady state, but as I told you that maybe m is not changing with time, properties are not varying with time, but their product may change with time. So, we have to ensure that steady state steady flow, that means their product will not change with time. So, you know whatever we have written, that the energy balance equation, that is first law of thermodynamics, in the rate form applied to the steady state steady flow process across the control volume. If we need to attain this equation, so this energy balance is not a balance in an isolated manner, but it has to be coupled with the mass balance, right. Because if mass is changing with time, then we can't say, we can't write that dE Cv dt will be equal to 0. So, basically this equation we can write only when product of mass and properties will not change with time. So, this is very important. Why I am telling this, because you know that we shall be using this equation frequently, maybe from the next week onward. So, before applying this particular equation, we may not get enough time to explain from where this equation is coming and why we are writing this particular equation in the context of that process. I am discussing this part. So, these are the critical part. So, you know that with this, so basically you should remember that this is the mass balance equation, this is the energy balance equation, and for the steady state steady flow processes, the energy balance is not a balance in an isolated manner, but it has to be coupled with the mass balance equation. So, you know that now what we will be doing is that so here, so to arrive at this equation, we have taken a few assumptions. First one is that properties are not varying over the cross sections through which flow occurs. Number 2, that is steady state, and number 3 is steady flow. So, considering all these, properties are not varying over the cross section through which flow occurs, state is steady and flow is also steady, and as I told you, product of mass and properties should not change with time. Okay. So, our product of mass and properties do not change with time. So, with this I would like to just complete the discussion related to the first law of thermodynamics, because probably you have studied another important process, that is unsteady state unsteady flow process, USUF. So, if the state is unsteady and flow is also unsteady, then what would be the form of the first law of thermodynamics? That is also an important equation, but as I told you that in this particular course several processes will be discussed, and whenever we would like to discuss all those processes, we will be taking this important I can say assumption is that the process is steady state steady flow. So, considering this, just I wanted to have this discussion that what would be the form of the first law of thermodynamics for the steady state steady flow process. So, before going to complete today's lecture, just I would like to briefly introduce that what is second law. In fact, a few classes in this particular course contents are designed in such a way that in the first a few classes we shall be discussing about the combination or combined first and second laws applied to several processes. So, before going to discuss that particular topic, let us briefly discuss about what is second law of thermodynamics. So, this is second law of thermodynamics. you have studied about two important statements of the second law, that is Kelvin Planck and Clausius statement. You know that before coming to those statements, I would like to recapitulate, although you have learned it from basic thermodynamics course, but I would like to discuss the need of the second law. You know that I mean, we have discussed about first law, then why second law is coming. So, definitely we need to know the limitations of the first law, and probably there are a few limitations of the first law, and it is because of this reason the second law of thermodynamics is there. So, why second law is important? We have talked about the first law, you have seen that it is the statement of the conservation of energy. Now, when we have discussed about energy transfer across the control surface, energy exchange between system and surroundings when the system is a control mass system, but it mostly talks about the conservation of energy, but it does not provide the directionality of the processes. So, basically we have talked about that if energy is given by heat to the system, we can take it positive. If work energy is coming out from the system by work, it is taken as positive, but whether the energy heat will flow from the surrounding into the system or vice versa. So, that means when you are talking about if work is coming out from the system, that is energy is coming out from the system by work, we can take it positive. That means if we take it positive, so there is a possibility that work might go into the system, right. So, that this directionality constraint cannot be described by using the first law of thermodynamics, rather by making use of the first law of thermodynamics. So, one issue is that second law provides the permissible direction of all the processes in real applications. So, this is one. Number two is you have studied that there are many properties including extensive and intensive properties. There are a few properties which you cannot directly measure. So, those properties are obtained from different thermodynamic relations. So, to quantify such properties like enthalpy, internal energy, we need second law of thermodynamics. So, first law cannot provide the quantification, rather the ways by which we can quantify those properties which are not directly measurable. Second is that as I was telling that in this particular course we will be discussing about different thermal systems. Say for example, if it is a thermal power plant, probably that there are several components in a power plant, and these components are there to ascertain that certain processes can be executed through those components. So, that when we talk about the thermal power plant, essentially one important part is the optimum design. Why? Because we need to know the performance of the plant. So, if we try to quantify the performance or thermal performance of the power plant, we also need to look at the performance of individual component which are there, which are integrated to this particular plant. So, to measure or to assess the performance of thermodynamic process, second law is used. So, basically if we have a compressor or if we have a turbine, so whenever the working substance is allowed to pass, like as I was talking about that flow process, it is not a non-flow process. So, when there is a flow process, whether the process is occurring in a compressor or in a turbine or in a pump, we need to measure the performance, we need to assess the performance. So, second law is used to measure or to assess the performance of thermodynamic processes. And another important objective is that you perhaps know that second law provides us the concept of an important, what I can say, absolute sense of quantity, that is entropy. So, basically entropy, the concept of entropy is essentially coming from the second law of thermodynamics. So, there are maybe a few more, but at least we have discussed a few objectives which cannot be described by making use of the first law of thermodynamics, and that is why second law of thermodynamics came into the picture. Now, you know that just describing the statement of second law like Kelvin-Planck statement or Clausius statement, I would like to recap those, but you have learned all those and you can get it from any classical book. So, you know that what is Kelvin-Planck statement and what is Clausius statement. So, basically I mean the concept of heat engine and heat pump or refrigerator. So, whether you know that if it is heat engine or if it is heat pump, the fundamental difference between these two cyclic devices is that one is work producing device, another one is the work absorbing device. So, we have seen whether it is a work producing device or it is a work absorbing device, processes are involved. In all those processes, rather cyclic processes, that are not fully reversible, right. So, some degrees of irreversibility are associated with the processes, whether it is a work producing device or it is a work absorbing device or it is a heat interacting device. So, to know some degrees of irreversibility is there. So, basically the process is deviating from the reversible process. So, to know the extent of the deviation of the process from the reversible process. So, second law of thermodynamics will give us a clue about one particular term which can be used to quantify the deviation of reversibility. So, when you are talking about irreversibility, that is I am not going to discuss, but the presence of irreversibility will destroy the performance of the processes which are there. Just for example, if we talk about that in a cyclic process there are three to complete a cyclic process there are 4 or 5 sub processes. In all these sub processes, if some kind of or some degrees of irreversibility is there, then it will definitely going to destroy the overall performance of the system. So, to know that we know that some degrees of irreversibility is there, but that means the processes are deviating from the reversible process. Now, to extend the processes are deviating, in what extent the processes are deviating from the reversible process we need to know. So, it is the second law of thermodynamics by which we can quantify, we can define one important term which will give us a clue about the extent of deviation of that particular process from the reversible process. So, with this and that aspect we shall discuss, I would like to discuss in greater detail before I go to discuss about the several other modules of this course, and this particular aspect we shall discuss in the next class. So, with this I stop here today. Thank you.